Next, we're going to talk about the gamma probability distribution. This particular probability distribution is often used in a number of situations, such as dealing with survival analysis or reliability analysis. So, for example, if y was a random variable with a gamma PDF, y could represent, let's say, the lifetime of some kind of manufactured product, or it could be, let's say, the lifetime of a particular kind of animal. And when I mean lifetime, I mean like when does the animal, for example, die? So y could be, let's say, 30 for 30 months. And so with this particular probability distribution associated inside the f of y for it, there is what's called a gamma function. This is a particular function, has nothing really to do with statistics itself. It's a mathematical function that's often used. Sometimes it's taught in a calculus class. But in case it hasn't been taught to you before, I just want to briefly review this particular mathematical function. So the gamma function is this. Gamma of alpha. So the function is going to change in terms of alpha. The integral from 0 to infinity of w raised to the alpha minus 1 times e to the negative w dw for alpha values greater than 0. Okay, so what's some practical, let's say somewhat practical places where this gamma function is used, or maybe you have encountered it before? Well, if this alpha is a positive integer, then gamma of alpha represents alpha minus 1 factorial. So the fact that it's how it's related to factorials is where most people encounter it. Now, one can also show by integration by parts that gamma of alpha is actually equal to alpha minus 1 times gamma of alpha minus 1. Don't worry about showing that yourself. Again, this is just a mathematical function, some properties of it. We will actually use this property later. To actually calculate the gamma function in R or Sage, there's actually a gamma function. Okay. So with that then, this is what the gamma PDF looks like for a random variable y. There are two parameters that control the shape of the probability distribution, alpha and beta. Both are greater than 0. And we'll see how alpha and beta control the shape shortly. So for f of y, and f of y is equal to, for y greater than 0, 1 over beta raised to the alpha power times this gamma function evaluated at alpha times y to the alpha minus 1 times e to negative y divided by beta. So beta could be 1, alpha could be 1, alpha could be 10, beta could be 20, and so on. The key is, and as you'll see, and hopefully you realize this through some other examples too for other probability distributions, we want to choose an alpha and beta that makes sense relative to a particular problem of interest. What's going to do best to describe a population with this PDF? What values of alpha, what values of beta? And we will spend some time this semester talking about how to choose that alpha and beta through using statistical methods. So, alpha is often said to control the shape of the PDF because it mostly influences the peakedness of the PDF. You'll see examples shortly. Beta controls the scale of the PDF because it influences the spread of the PDF. In other words, how much are the y's spread out, possible values of y spread out. Now, one can show that the expected value of y is equal to alpha times beta. The variance of y is equal to alpha times beta squared. And how does one show that? Well, one goes back to what we learned before, where we take the integral from negative infinity to infinity. This is for the expected value of y. Take y times f of y dy. And if we want to, though, represent it in a general form of alpha and beta, that's where we need to do stuff symbolically. So let's actually go through the proof for the expected value of y. What this proof is going to take advantage of is something similar to what we saw with respect to the binomial distribution when we were finding the expected value of y for that. In that case, if you remember, we tried to get the stuff in the sum to add to 1. Here we're going to try to get the stuff in the integral to integrate to 1. Okay, so the integral from 0 to infinity of y times f of y dy. Well, this y then can be put into this part right there, and that's what I did. And hopefully you see that, oh, okay, this looks kind of familiar. It's almost like a gamma distribution that we just saw. But now, here, if I had the parameter of alpha plus 1 for that place, I would have the gamma. I would need to fix some stuff, though, out here, though, but I could have the gamma distribution. And then perhaps use the fact that the integral of f of y dy from 0 to infinity would be equal to 1. Okay, so let's look at how we can use that kind of a property. Okay. So what I would like here, this part right here, I would like that to correspond to a gamma distribution that still had that parameter beta, but also has another parameter that symbolically is just alpha plus 1. And so to do that, I'm going to multiply and divide by gamma of alpha plus 1 times beta raised to the alpha plus 1. Now note, by me multiplying by that, it doesn't change anything in terms of what this equality is, because this is all equal to 1. The numerator is the same as the denominator. But what I'm going to do is I'm going to now factor this part out, which is just a constant, and then push this part in to the integral. And this is what I get after doing it. Now this whole part here in this integral is like f of y itself, but now for a different kind of gamma distribution with parameter alpha plus 1 and parameter beta. And so then this whole part then is equal to 1. And we're left with then this beta raised to the alpha plus 1 times gamma of alpha plus 1 over beta to the alpha times gamma of alpha. Okay, we can do some simplification here. This alpha there crosses out with that alpha. So it's like saying, let's say, 2 to the 3 over 2 to the 2 is equal to 2. And then this gamma of alpha plus 1 divided by gamma of alpha. Now I use this one of these properties that I mentioned before. This gamma of alpha plus 1 can be simplified to alpha times gamma of alpha. Once I do that, I cross that out, and I'm left with just alpha times beta. You can do a similar proof for the expected value of y squared. And once you do that, then you can get the variance. Okay, let's take a look at some basic calculations with the gamma PDF. First of all, this is a d gamma function. It's what finds f of y for us. So this d function works similar to what we've seen with other functions like d norm. And if I wanted to, I could set up a function called PDF in R that allows me to evaluate f of y, where I'm going to pass in information in addition to y. We're going to pass in alpha and beta. And if I were to then integrate this PDF from 0 to infinity, and let's say I choose an alpha beta of 1, I could have chosen something else. Guess what? I get this to integrate to 1, as we would expect. To actually calculate the CDF in R, we can use the P gamma function. So if I wanted capital F of 1, in other words, the probability y is less than 1, I can use the P gamma function. The quantile is, let's say, 1, corresponding to that right there. Sorry to have so many 1s floating around. My shape parameter, sorry, I should have mentioned that before. My shape parameter is going to be alpha. My scale parameter is going to be beta. I get 0.63. So that's the area underneath the curve to the left of 1. Alternatively, what I could have done is just simply integrate. But of course, using the P gamma function is going to be easier. Okay, in this particular program, I have it set up so that you can explore graphs of the actual PDF. And so let's look at this particular case where beta is equal to 1. But I'm going to allow alpha to vary from 1 to 2 to 3. And what we can see here is that that peak of that distribution is changing as a function of the alpha that we see there. And if we take a look at another plot where alpha is fixed to be 1, but now beta changes from 1 to 2 to 3, we can see how that peak type still stays the same, but now more so the scale of the distribution in terms of how spread out everything is changes. So this is why alpha and beta are often called parameters that control the peakedness and also the scale, respectively, of the probability distribution. Again, on your own, explore a number of different alpha and beta values so that you can see how this changes. And again, always to yourself, think about why we are doing this. And that is, we are trying to characterize how items in a population are distributed, such as how long of a life a particular maybe animal or a manufactured part for an airplane actually will last. When you do that, also take a look at how this all affects then the mean and the variance as well. And we can see that, again, as alpha and beta change, that probability distribution is going to change, and we will want to somehow come up with a good way to come up with a good alpha and a good beta, which we will talk about later. Okay, so let's take a look at this example then. Let's let y be a random variable denoting the lifetime in months of a particular type of animal in a population. Suppose it follows a gamma PDF with beta equal 15 and alpha equal 2. What I mean by follows, it can be characterized by a gamma PDF. This is what the PDF looks like. And so that we can see here, it would be very unusual to have a lifetime that is greater than 80 months. It would not be unusual to have something, let's say, between 20 and 40, and so on. Let me do some erasing. Okay, with that setup then, well, what's the mean and the variance? Well, the mean would be expected value of y, or mu, which would be alpha times beta, or in other words, 30. And so here's where 30 falls on the plot. And we can see how it's kind of in the middle of the distribution. It's not where the highest point of the distribution is, because notice how this probability distribution is right skewed. And back when we were talking about a sample mean and a sample median with respect to skewness, refer back to that discussion for why it's not unusual for the mean here to be a little bit farther to the right of where you see that highest point. What is the probability an animal in this population lives longer than 80 years? So again, here's that 80, and we can see that's going to be very small. If my calculations gave me something that wasn't small, then I would have to question if my calculations were right. So how would we find this value? We want to find the probability that y is greater than 80. In other words, integrate from 80 to infinity of f of y dy. Or we could turn things around. Again, use the complement. So we have 1 minus the probability of y being less than 80, which is equal to 1 minus the CDF evaluated at 80. How do we get the CDF? Again, the P gamma function. And so I can put in my value of alpha. I can put in my value of beta. Here's my quantile, that 80. Do the calculations, and we can see that this probability is very small, 0.03. Well, what about the median lifetime? Again, think about what the median means. It means half the time you're less than this value, half the time you're greater than this value. In other words, find the value of c that satisfies this expression here. The probability y is less than c is equal to 0.5. I guess if I wanted to, I could have used the letter Q to correspond to quantile, because what we're trying to find is actually the 0.5 quantile. So if we did want to do it in terms of C, we would simply do the integration from 0 to c of f of y dy, then set it equal to 0.5, solve for c. Or simply go to the Q gamma function, and what do we get out? 25.17. Let's go back to our plot. Here's where 25 is. Notice how that is to the left of the mean, and based upon what we learned earlier about means and medians, with a right skewed distribution like this, this is what we would expect. Well, what does a sample look like in this kind of a scenario when I have a population characterized by this particular PDF? Well, let's take a sample 1000 to take a look at it. Similar to how we used the R norm function before, we can use the R gamma function now here. So I can set a seed so I can reproduce my results. Again, I can choose any number that I want. I just happen to choose this one. Then y is going to get the results from the R gamma function, where I want to sample a size 1000 with my alpha to be 2 and my beta to be 15. If I use the head function to look at the first 6 of these sample values or observations, the first one had a lifetime of 50.9 months, the next one 23.7 months, and so on. I can use the mean function and the variance function to find the sample mean, the sample variance, in other words, y bar ns squared. And let's compare that to what we would expect. Again, the expected value of y is equal to alpha times beta, or 30. And we get something similar with our sample. You can do the same thing with the variance to confirm that. And so again, the purpose here, and perhaps I'm saying this too much, is to help you see what does it mean when a population is characterized by a PDF. What it's saying is that if I did take a sample from that population, it gives me an idea of what to expect to have happen. Also, what I could do is I could look at, let's look at all those y's, all those lifetimes that were greater than 80. So if I did y greater than 80, then that's going to return 1000 trues and falses, corresponding to if a particular value of y in my sample is greater than 80 or not. When I do some kind of mathematical function with these trues and falses, R converts them to ones and zeros. So if I took the mean of them, I get the proportion of ones out of these 1000. In other words, I get the proportion of these y's that are greater than 80, which is 0.03, very similar to what we found before with that particular probability. I could also do a histogram of the sample too, so that I can plot the actual PDF on it. I'm going to use the freq equal false argument so that it rescales the y-axis. I plot then the corresponding PDF using the curve function, where I use d gamma to get me my f of y. When I do that, we can see that, yeah, this histogram follows the same shape as what we get for the actual PDF itself. Again, this is what we would expect. This shows you what it means to, again, characterize a population by a particular probability distribution. I could also do the CDF as well. So I can plot the empirical CDF on the same plot as the actual CDF, and we get agreement between the two, as we would expect. Now, there are a number of special cases of the gamma distribution that pop up in actual application. We'll talk about one of them later in the semester, but we've already actually talked about another one of these particular special cases, and that is for what's called an exponential PDF. So an exponential PDF in a general form looks like this. F of y is equal to 1 over beta times e to the negative y divided by beta for y greater than 0. And also beta is always going to be greater than 0. This is the same PDF that we used for that transaction time example where beta was equal to 30. So Why is this a special case? Simply, alpha is equal to 1. Here's a nice general plot of what it's going to look like. If you put y equals 0 into f of y, look what you get out, 1 over beta. So that's the highest point of that PDF. The mean and the variance of this exponential PDF correspond to as you would expect, because alpha is equal to 1. So the expected value of y is beta. The variance of y is beta squared. So as I just mentioned a minute ago, we used this particular PDF when we were working with the transaction time example. Beta was simply equal to 30 in that particular example. And so you can go back to all those past calculations to see how we actually did them so that you get experience with the exponential PDF. Now, similar to what we have for the gamma PDF or the normal PDF, there are actually specific functions available to you in R that allows you to then do various calculations with the exponential PDF. In particular, there is a function called DEXP. And what that function is going to give you is your f of y. But be careful when you use that function, though. Rather than having the scale argument like we had with the gamma function, it has a rate argument. Actually, the d-gamma function does as well. And what the rate argument corresponds to is 1 over our beta. The scale corresponds to beta. So you can get into trouble if you don't pay attention to that relative to how we've defined the PDF. So with that then that concludes in this section on the gamma probability distribution.